Hello, everyone. Welcome to the Audio Product Development Alliance. I'm Roger Shively from Shively Acoustics International, and this is the APDA, your gateway to the audio product development. So I'd like to introduce everyone from the Audio Product Development Alliance. We're a team of audio industry experts who are committed to furthering the techniques and skills of professionals involved in developing audio products. And we want to focus on promoting methodologies and practices and technologies involved in the developing and bringing the audio products to market. And what we try to do is we try to build better relationships so we can build better audio products and talk about design, measurement, simulation, supply chain, automotive applications, headphones, earphones, wireless technologies. And we even touch on industry standards, of course. And online today with us is from the APDA are Steve Willenberg from LinkPlay, and we have Dave Lindberg from the THD podcast. Our media partner is Audio Express, and also we are joined today by Jacob Sonnegaard, who is the customer success manager at Head Acoustics. We're going to be recording today on YouTube, and you can check us out on YouTube channel, like us there as well, and you can watch this later on the channel. Jacob's topic today is going to be active sound design and listening effort in vehicles, and how to measure and evaluate the effects of active sound design in vehicle interiors. So welcome, Jacob. I'm glad you're here.
Welcome,
Thanks,
Jacob.
thanks for joining us.
Happy to be here.
Yeah.
Right.
So today we're going to try to discuss a little bit about the impact and the interaction of audio systems in the car cabin over communications and privacy. And we're trying to learn a little bit about evaluating listening effort using some of the standards that are out there for analysis methods. And most of those, I think, use real speech for analysis. And then how to analyze the potential impact on communication between passengers resulting from active enhancement systems that are used in electric vehicles. So I'll let you get started. And as we start, perhaps you can give us a little bit of the motivation of the study that you had done and the information that you're going to share today.
Yeah, I'm happy to do that. I guess the bottom line is that I'm here to present a little bit about something that I think is unique in the industry, something that's a little bit interesting, and hopefully stimulate some good thought and discussion. But it's really about looking at technology in a car and how we can take steps towards making acoustic zones, or bubbles, as it's sometimes called, in a car. And in order for us to achieve this bubble situation, there's a couple different things that are currently happening in the automotive industry. There are some adjacent technologies that we can borrow and apply, and then there are some metrics, and we're going to roll all that together, bake a cake, and then have some fun with it. So this presentation is really about, peeling back some of the layers in all of this, and hopefully make a little bit of an enlightening talk that stimulates people to go and look at this further.
Okay, good. Let's jump in.
Roger, before I go, can you just confirm you can see my screen?
Oh, we can see it.
Perfect.
Looking good.
Perfect.
Looking good.
All right. So let me just start by saying that the modern car is driven by, and I like to say voice, but there's a lot of technology in a modern car, and specifically it is housed in the head unit. The head unit's kind of like the heart, mind, and soul of a modern car. It's not just for music and hands-free calling, but it's also important features for the user interface, and elements that create a positive outcome. So I'm starting to populate this little vehicle with a whole bunch of different bubbles here with technology. I won't go into a tremendous amount of detail on each of these, but the thing that I really want to emphasize today is the active sound design component, ASD. I'll refer to it as ASD quite often in this presentation. And I'll talk a little bit about active sound design, what it is, how we use it, and how it plays a role in the car, and then also in-car communication systems. generally in-car communication, as well as systems that could be implemented in the car. And the key thing that I'm going to be relying on for my evaluation is something that we call listening effort. It's sort of akin to intelligibility, but we'll be using that metric to just look at how ASD and ICC functions in a car. The other technologies are related. They're interesting. We'll maybe just touch on them, but we won't go into a lot of detail on those. So first thing, active sound design. What is it? So if you have a electric car, specifically an electric car, the reason why we choose electric cars is A, they're becoming a lot more popular. B, they don't have an internal combustion engine, ICE, an ICE engine anymore that generally creates a lot of noise, masking noise as such. And so now in an electric car, all the noise components from an electric car are going to be a lot more noticeable. And they generally don't sound the way that we expect a car to sound. So it's different for people sitting in the car. And what active sound design is doing is it's using these sensors in the car. So this could be vibration sensors, certainly acoustic sensors, pressure sensors, etc., to gather information about the sound field in the car, apply some fancy math and FFTs, etc., to create a, let's call it an artificial sound. Artificial sort of has two meanings. Number one is artificial means fake, but it also means something that's sort of created from scratch, something that doesn't exist to begin with. The goal for us is to create something artificial that is good, but we create this sound actively based on information in the car, and then we play it out of the loudspeakers in the car such that the vehicle occupants are now hearing a slightly modified soundscape or sound environment that sounds could be more pleasing, it could be safer, it could just be generally less harsh. There's a bunch of different reasons why we would do apply active sound design techniques in the car, but those are just a quick handful. So that's like the 60-second intro to active sound design. The other one, in-car communication. So specifically for drivers in a car, specifically for drivers in big vehicles, three-row vehicles, it can be very difficult to communicate with the people in the second row, or especially in the third row of the vehicle. And what we don't want to happen is to have the driver turn their head around over their shoulders, look in the back row, and start talking to the people, right? Because the way that speech emanates from the mouth is it's fairly directional. Unlike a loudspeaker, we are very directional creatures when we speak. And if you're the driver and you're looking straight ahead, most of your speech is propelling straight forward and not into the back seat. So we have these fancy systems called in-car communication systems that uses the built-in microphone up by the driver. Typically, it's located in the visor in the center console above the driver. And then we apply some noise reduction and some AGC and echo cancellation and equalization. Those are all the little acronyms in the yellow box. So then we do this very quickly, and then we play out the speech in the back seat such that whatever the driver said is being amplified without any of the driving noise or any other noise in the car into the rear of the cabin, and they can understand what the driver is saying without them having to elevate their talking effort and having to yell. It would lead to a more natural conversational experience. So those are sort of the foundational technologies that I wanted to touch on. And then I wanted to get into this listening effort. So listening effort is a standardized metric, standardized in ETSI TS 103558. That is a publicly available document, so anyone can go to that website. And ETSI is, of course, not the crafting home supply website. ETSI is the European Telecommunication Standards Institute. But the bottom line with the listening effort metric is that we have a 5-point scale. This is known as a MOS, mean opinion score scale, that tells us how easy it is to understand speech given the existing circumstances. And with all MOS metrics, the score goes from 1 being the worst, 5 being the best, and specifically the qualitative And the subjective markers associated with these, as you can see on the screen, a 1 means it's just impossible to understand what's being said, and a 5 means you can do that in a completely relaxed state. So quite a large span, but the thing with mean opinion score algorithms is that they're based on a jury study. And so at one point in time, we had hundreds of people come in, sit down, listen to speech samples, and they gave their opinions, their opinion score in integer values. And once you collect enough data points from all these people and all these different speech samples under all these different noisy and reverberant conditions, you can then build an algorithm that takes the mean opinion score of all of these people. So every time you run the algorithm, it's like inviting 300 of your favorite friends to come in and listen to this sample and then determine how easy is it to understand the speech given these conditions. And that also means that we don't stick to just integer values. The listening effort metric does give us decimal point values and more granularity.
And I'm sure you'll cover this. So the high and low, the examples, the circumstances, what does that mean in terms of a high effort and a low? What are the situations that we get into that might influence us to have difficulty with our effort to
Yeah,
listen?
in short, anything, I think the key word is masking. Any type of environment, acoustic environment that masks the speech is going to create what we call a high listening effort scenario, meaning a
Mhm.
low listening effort score. So it could be noise, it could be reverberation, it could be a combination of both, it could be multiple talkers, distractors. Noise
Mhm.
doesn't have to be noise, it could be speech or even audio or music for that matter. It's just things that are masking the speech. And then on the opposite side, the lack of such elements would lead to a high listening effort score, meaning low listening effort. And there are technologies that you might be familiar with. So like ANC systems and a pair of headphones, they help block out the outside noise. That's a very common example for improving the listening effort situation if you're trying to enjoy, say, a podcast or you're on a phone call or listening to a webinar. So bottom line is this is a key metric that we are looking to apply here and also apply in a slightly different new way that I'll go into later in the webinar. But the standard's free to download. So for those that want to do the deep dive, hit the link for EVSE and go fish out the standard.
And Jacob, just a quick question with regards to the automotive companies. They've bought into the methodology and process of this technology.
So the listening effort standard is governed by EVSE, but it's also being applied in different industries for industry specific applications. So for instance, for emergency calling features and hands-free calling, the standards are starting to adopt the EVSE standard and saying, use this metric for evaluating whether your system's actually doing what it's supposed to do, which is ultimately producing a conversational experience that is easier for people to exist in.
I understand. Okay. Thank you.
Yep. All right. So now let's look at voice and then designed noise. So first of all, why do we need active sound design? So in many cases with vehicles, whether they're on the road or in the air, we'll do what we can mechanically and what we call passively to work on the individual noise sources and the noise components, but it's still good to avoid the weight penalties that come with having too much acoustic treatment on board for that cabin noise control. Like nobody wants to put an anechoic chamber in a car. It's going to be way too heavy to drive around with. And so from a manufacturing standpoint, it reduces complexity, it improves fuel economy, manufacturing costs go down, etc. if you ease up on some of the passive sound design. But that still means that we end up in an environment that's maybe not the best inside. So in an electric car, when you remove the ICE engine, the ICE engine, what do we have? There's all the electric components, the motor, transmission, inverters, etc. But then we also have the road and the tire noise. That doesn't go away just because we're in an electric car. That's still there. And we have the wind noise or the aerodynamic noise created by the shape of the car, especially the mirrors and the windshield are big contributors. So in the grand scheme of things, there are really only those three primary noise sources, road, wind, and electric, but neither of them really, when you think about those noises, they don't really scream power or confidence or anything like that. It's just sort of annoying sounds in there. And we should think about how potentially some of these noise sources could interact. So think about some electric vehicles have a main central hub motor. Some of them have distributed motor systems sitting in each wheel or hub location. There's a funny possibility there for sort of randomly shifting modulations at each of the wheel locations, or rather the motor locations, that produce sort of a family of tonalities that aren't exactly the same pitch, but close. And on the one hand, that could lead to sort of a subtle swarm of bees effect that could organicize, that's a word, the sound, and make it a little bit more interesting and less toxic to the human ear. Or it could be very grating and irritating and not really invoke a very good sensation at all in the car. So the bottom line is, with active sound design, obviously it is a relatively inexpensive way to improve the user experience in the car, both from a manufacturing standpoint, because you're not really adding a lot of weight. You're using the audio system that's in the car anyway, and then some processing power and engineering specialties, of course. But what we want to do is we want to replicate sort of real world scenarios. Music, nature, and real systems and real spaces, they all provide complexity and sound. And the challenge for us working in cars with active sound design is to do something positive and pleasing. Like still create that complexity, but it sounds good and it sounds satisfying when we're just using these electronic strategies in sort of a virtual space inside of the car cabin.
So
And
when you're
just
go ahead,
curious,
David.
does this must intertwine with some of the automotive safety standards? I can imagine if you go with a perfect active sound design, you might not hear anything in your awareness, kind of like the occlusion effect in headphones. So is that also a complicated thing for manufacturers to intertwine the safety and occlusion versus making a nice experience inside the cabin?
Yeah, generally, I mean, yes, it's a consideration, but generally the way that ASD has been implemented so far has not been to such an extreme extent that you would override safety indicators or I mean, it's something to be aware of, but generally it's not that extreme. It's a little bit more subtle. And
Okay.
that's been good so far, but yeah, you don't want to miss like a lane drift warning or somebody in your blind spot or something like that. That would be very bad because now you're defeating, the safety purposes of the vehicle.
Yeah,
Sure.
that goes to a question I had when you talk about sound design, and perceiving is what we're going to talk about, but quickly to understand what it is we're trying to perceive. You're trying to perceive adding a sense of movement or sound in the car that doesn't exist anymore, make it more pleasing so that some of those unpleasant sounds are masked, but not to mask the speech that might be coming throughout the car, or also these emergency vehicle warnings or emergency warnings. So
That's correct.
that's what active design
That's
is for. Is
correct.
make it pleasant, but you're not trying to make it sound, well, maybe you are trying to make it sound like a loud rumbling engine anymore, but you're trying to make it a pleasant sound or whatever your goal is. So that's what
Yeah,
we're talking about. Okay.
you're spot on, Roger, and I'll get to that. Maybe I'm spending too much time on active sound design, but
That's okay. Yeah.
I promise I will get there. Um, what I did want to show was a specific example of what active sound design would look like. And if we weren't doing this live on the internet, where I'm questioning whether I can transmit audio that mostly sounds like noise because of noise suppressors, etc., people will have to use their imagination. But what I'm showing you in the bottom left-hand corner is a spectrogram. So x-axis is time, y-axis is frequency, and then the color is the magnitude of it. This is of a car basically accelerating from 0 to highway speeds, electric vehicle, no active sound design on. And when you listen to it, it sounds like you would imagine. It sounds like an electric car, just like a blender whirring up, nothing too exciting and interesting. And then on the far right-hand side, this is what our active sound designers came up with. And so they created this based on what the vehicle sounds like and then match that to the throttle position such that when you accelerate, you get sort of that top left, the merging of the two. It's the original electric engine noises and the road noise and the wind noise in there, but you have this layer on top of it, so it sounds a lot more powerful and a lot more present. And we're doing different things, using different tricks like shepherd tones, if you're familiar with those, like infinitely rising tones called shepherd tones, or using major thirds for sound coloring. Those are some of the techniques that are being used. Now, what I would like to do then is jump into an actual car that we used for this measurement. It's a right-hand drive car. So our friends in Japan, UK, Australia will be pleased. The rest of us, we have to flip our brains a bit. So driver's side front. So that's top left. They are getting the following spectrum when the ASD is active. And what you'll see just looking at this is that this particular vehicle had a subwoofer in the rear of the car, and the subwoofer is producing a lot of the lower frequency content that's used in the active sound design. So the rear seats, in particular, the driver's side rear, so that's the top right on the slide, is going to be exposed to a lot more active sound design than everybody else in the vehicle. I don't know how well thought out that is. We'll go and analyze and take a look at it. But then the question is, if you're an active sound designer, keep in mind, where are your sound sources and who are you designing this for? Is this primarily for the driver, or is it for the other occupants, the passengers in the vehicle? If you're not careful, you could end up with this asymmetric and uneven active sound design for each of the seat locations. So let's look at the two different scenarios that I want to dive into. Number one, I want to look at this in-car communication. How easy is it for the driver in our right-hand drive vehicle to communicate with the other occupants in the car while they are driving? And then the other one I want to look at is using a hands-free system, so making a phone call and applying the listening effort metric here to gauge privacy and take that one step closer to the zone and the bubble technology. So first up, let's look at this in-vehicle scenario. We're equipping the car with a whole bunch of head and torsos. The driver will be able to rotate its head around, and then we will use our listening effort metric to evaluate the different conditions. So the two conditions that we chose was a steady state 60 kilometers an hour, is about 40 miles an hour, steady cruise. What you're seeing, that's in the middle of the slide. On the orange, what you're seeing there is the level versus time of the vehicle noise with the active sound design system switched on. And in the blue right below it, 2 dB down, you have the active sound as the level versus time with the active sound design off. On the right-hand side, we have this speed, the ramp up, ramp down scenario where you go from 50 to 100 and then 100 to 50. So about 35 miles an hour to 60 and back down to 35. There, the active sound design is a lot more prominent. So we're actively and aggressively using the throttle to modulate the speed of the vehicle. And so the active sound design is a lot more aggressive. So those are our two different scenarios. And what we do now is we insert speech sentences. So what we call Harvard speech sentences, Harvard sentences. Harvard, because I think they were originally created at Harvard, but what they really mean is that the speech sentences are phonetically balanced and they stress all the elements and sibilances of human speech within our given language.
Yeah,
so
these were used for
it uses a mix of male
telecommunication.
speakers and female speakers.
Yeah, yeah. They were using telecommunications to test communication
exactly.
across long transmission lines. Yeah. Okay.
Yep. So we're inserting these strategically at different points so we can evaluate this particular speech sample under these given noise conditions. So first one, let's look at the driver's side, looking straight forward at the constant 60 kilometers an hour. And what we end up with is when we evaluate the listening effort at each of the seat positions, we see that the passenger has a fairly easy time. So remember, on a scale of 1 to 5, 4 is very good. There's almost no effort required to understand the driver at 40 miles an hour, give or take. The rear is struggling a little bit more. That's natural because they're in the back of the car and the driver is talking straight forward. And with the active sound design on, we're not seeing that big of a difference between the listening effort in these locations. Does that make sense? Good. All
Sounds
right.
good.
So next up, the ramp up and ramp down. So now we're modulating our speed. And as we remember, the general level versus time profile in the car was about 5 dB higher. And so now we're seeing significant differences, especially in the driver's side rear position. There's half a MOS point difference in the listening effort, and we're getting into the 2.4 range. So now we're using a considerable amount of effort to understand what's happening, what the driver is saying if we're sitting behind the driver. So the driver now has two choices: speak up or start yelling, or very inadvisably turn their head, take their eyes off the road and turn and then start talking to the side. So we simulated this because we know drivers do this. In this case, what we're seeing is that the listening effort for the ramp up and ramp down situation is very high at the passenger side front and the passenger side rear. But we're still struggling with the rear seat behind the driver. Now we're seeing almost a 1 MOS point difference when the active speech or the active sound design is switched on. This is a very unfortunate situation because the vehicle subjectively sounds better when the active sound design is on, but it's making it nearly impossible to have conversations between the driver and the driver's side rear passenger, even if they rotate their head and turn around and look, which is not advisable.
All right, that's interesting. So that's with the sound design. Then we have the you're going to the communication effort. Go
Yep.
ahead.
Yep.
Yeah.
So let me look at the communication side of things. So on the communication side of things, again, we're interested now in looking at acoustic zones and privacy. And what we are proposing is we should use the listening effort metric to evaluate the privacy from one seat location to another.
Is there any method now that or a standard now for that type of how private is private?
There's not.
Okay.
That's part of the problem. There really isn't. And part of this message is to maybe open some eyes or ears to the fact that there is a metric that we can use sort of ironically in reverse to gauge the privacy of these individual zones. So let me set the stage here and say in a typical car, you have, when you're engaged in a hands-free call, you wouldn't typically use the entire audio system for speech transmission in what we would call the receive direction. So when the far end is talking to you in the car, you would typically only use 2 loudspeakers at the front, maybe the entire A-pillar set of speakers at most, but it's a very symmetrical implementation. And so if it is symmetrical, as you can imagine, both the driver and the co-driver location would essentially get the same speech at their ears.
Mm-hmm.
So these two guys here would hear exactly the same thing.
Got it.
That means that there's zero privacy. So if you're having a phone call with your bank or a business partner or your doctor, and there might be information that you don't want everybody to hear, this is not a good solution. It doesn't work the way that we intended. But if we employ what we call headrest loudspeakers. And this is a technology that already exists in some vehicles, and they are implementing it in airlines as well.
Yeah.
First class, mind you, but
Yeah.
you know, baby steps. And this is a technology that's aggressively being pursued in places like EVTOL, electric vertical takeoff and landing craft.
Okay. Okay.
Think like personalized helicopters,
Yeah,
helicopter taxis, that type of stuff.
you got it. Yeah.
If we now employ this headrest-based speaker technology, we can now tune that to provide exactly the same response at the driver location. So for this example, I'm back to a left-hand drive vehicle. So this is the
Okay.
driver shown in the pinkish curve.
Okay.
And when we play that pinkish curve out of the headrest speakers, all of a sudden, the response at the co-driver is drastically reduced. And that makes sense because the speech is now localized here. Rather than in the entire cabin of the car, it is now
Right.
localized right at this location. What we're seeing is roughly a 9 dB attenuation from one seat location to the other. So to put some numbers on that, that means the headrest of the driver shown in the pink is, we tuned it to be roughly the same as the driver's side speech when we were using the doors, but the co-driver level was dropped. That makes sense. No, for our little experiment, we just used some commercial off-the-shelf little loudspeakers, not really tuned for this particular application, but just to give you a sense of how even hacking something together can produce something quite dramatic. So at idle, so this is in complete silence. Remember, there's an electric car. When you're idling, there's nothing going on in the car. So it is silent. What you're seeing is that the listening effort for the driver is a 4.6 using the headrest mounted speakers. That's even better than what it is using the door mounted speakers. So that's positive. Maybe not quite intended, but it was positive. And the listening effort at the co-driver position is now dropping to a 3.4. So there's some moderate effort required by the co-driver, but the co-driver would be able to understand what's being spoken to the driver.
Okay.
That picture changes once we start moving. So if we speed up and we go 80 kilometers an hour, about 50 miles an hour, we're now seeing that, yes, there's more noise in the car. Active sound design is present. Wind and tire noise is there. But the driver's side listening effort is a 3.1, so moderate effort, but you can understand it pretty clearly. And the co-driver drops to a 1.6. So we're getting very close to that point where under no circumstances can the co-driver detect what it is that's being presented to you as the driver. And likewise, when we go even faster, sure enough, the results are about the same. It's pretty much impossible for the co-driver to figure out what's happening. And so this begs the question of what type of technologies, what type of improvements can we get to the acoustic space inside of the car if we start implementing individual zones and individual bubbles using headrest loudspeakers. So one that I wanted to just emphasize right here is, for instance, hearing assistance. So imagine that the car is aware of your profile, your hearing profile, not just your physical dimensions. So most cars, when you step in, it'll recognize who you are and it'll adjust the seat location and the steering wheel location to you. It could also specifically tune the audio response to compensate for any potential hearing loss that you're dealing with. And that would be unique to your seat location, just like the co-driver or any other passenger would be able to experience basically a better sounding system because it's tuned uniquely or individually to you in that location.
Okay.
So in general, when we talk about zones and privacy, also think about what ANC could do. And In-car communication systems. I didn't really touch on it too much, but when you're talking about communicating within a car, those in-car communication systems can generally give us a 1 MOS point improvement in the communication from the driver to the rear. So think about how much the active sound design degraded the communication experience. Is about 0.9. An in-car communication system would basically be able to rectify that loss because of active sound design.
And so you're talking about speech, which is clearly in the 200 to 8K range or so.
Yeah.
Music is also what some of the audio systems are trying to create personal sound zones, but this method is a way to detect not privacy so much as leakage or what have you between seats as well. So this could be a good way to test it in terms of not just the fundamental technical parameters, but this is a way to subjectively evaluate or perceived privacy, even for music or just for voice at this point. So.
No, you could, so good question. What I've done is we've looked at using speech in
Okay.
this case.
Yeah.
And that's because the listening effort metric is designed around speech in masked situations.
Got it.
The technology itself can just as well be used for isolating music playback. So there's
Okay.
no reason why each seat location couldn't have music streaming or a podcast and somebody on a phone call, like each seat location having something unique and individual to their seat going on. The problem is that we couldn't use the listening effort metric to evaluate how easy it is for another seat location to detect music because it was never trained for picking up music.
And I think the primary use case right now for headrest speakers are for those private calls or in-car communication improvements as well. So I think that's the main use case in these days. You know, there's an attempt to create a sound bubble for music, but you know, you may say that that's a trend coming, that you see it coming. But first, we need to find a good way to try to measure it all, other than sitting in the car and being very subjective about it. And this is a good way to do it on the road, in motion. So that's good.
Yep. So I'm really coming to the end of my presentation, and I think some of the things that I want to just wrap up with is that this concept of acoustic zones and bubbles we're really just right at the beginning of it. This is just an emerging technology. It's only just rolling out to some consumers. So generally, as I mentioned, some first class seats are getting it on airlines. Certain manufacturers are adopting this technology. They're looking at it for trains and public transportation scenarios. But this is an exciting time for audio and acoustic engineers. And, frankly, there are people that work on passive and active sound design and noise, on a daily basis. And I think this is a little bit of a new frontier for people to get into.
You mentioned active noise control, which is ANC, active noise control.
Yes.
It's similar in a way because you're canceling noise in that case, whereas maybe you're adding noise with the sound design. It's the same issue. You see that there is listening efforts because active noise control is also being played through loudspeakers, and the whole purpose of this in cars is to take out the heavier passive materials that can block noise, and in the case of an engine can reduce it, but with a speaker. But without the engine, now you have all these other noises. So with active noise being played through a loud system, an audio system, much like a telephone call might be, or engine sound design might be, there's an effect there because you're trying to cancel sound. You're also canceling intelligibility, or what's happening?
Yes and no. I mean, that's such an interesting topic, and basically that could be a whole nother presentation, a whole nother webinar, but I would like to address it because ANC, active noise cancellation, and RNC, road noise cancellation, are both super important technologies that we're still trying to figure out in the automotive space how to apply this strategically, and especially with the headrest technology. How do you balance that, and at what seat location do you implement this and how do you do this well? And you have, physics come into play here with lower frequency sound waves, etc.
Exactly. It's similar to the problem with music because music isn't going to, not necessarily be limited in the headrest. It depends on how you implement
Yep.
the low frequency content in your seat.
Yep.
But active noise control, I mean, clearly when you put in headrest, it's augmenting the higher frequency cancellation because you may not get past 1,000 hertz for some of your active noise control on the road even. But if you
Correct.
can add a headrest, you get this better correlation, and so it has an effect. And so I think you have a way of at least starting to look at how can you evaluate all these possibilities. And I think that's was the motivation for you to how can we quantify good or
That
bad?
and
Yeah.
I think you hit it on the head there because one of the things that's a little frustrating to me sometimes is that when we talk about ANC across industries, the effectiveness or the performance of the system is typically expressed as a function of dB or peak level reduction or something like that.
Yeah.
But these systems do play a really important role in reducing the amount of listening effort in a conversational experience by taking away noise. And I think the listening effort metric is a way to attach a subjective scale to the performance of a system like ANC or RNC, really regardless of application.
Now, the existing methods for evaluating clarity are sound transmission indexes.
Yep.
So where does this sit in that relationship?
That is a
Another
good
one.
question. This is where we put on our standardization hats and also our detective caps because we got to go back in time to when these algorithms were designed. So speech transmission index and all of its variations like RASTI and so
Yeah.
STIPA and there's a bunch of them. There's a speech intelligibility index, and there's an articulation index, not to be confused with the AI term we all throw around today. But a lot of these were designed and standardized in the 60s and 70s, and for different reasons, for varying reasons, many of them, actually all of them, aren't really applicable to these scenarios where we're talking about, communication. So some of them use simplistic stimulus signals that would not be passed through a sophisticated system that is designed for transmitting speech, for instance. Others split the way, so it's like a two-step method where first you measure the noise and then you measure the speech and then you do some basic weighting and computation. It doesn't work because the system's not being stimulated by noise and speech at the same time, which is the operating condition that you're trying to measure. So the system behaves differently during the test than during the real world. And that's frankly part of the reason why the ETSI group got around to standardizing the listening effort metric, because all of these other metrics for various reasons sort of fall through the cracks of what we're trying to accomplish with modern communication systems that employ sophisticated noise suppressors and voice activity detectors, etc.
No.
So there's a lot of information you can go and pick out. NCS 3.5 I think is the SII standard, but we little shameless self-promotion, but Head Acoustics wrote an app note that sort of outlined why some of these metrics of yesteryear aren't quite appropriate anymore and how the listening effort one sort of separates itself from those. So that's available on the website for those that are interested.
Yeah, and they could probably find you on LinkedIn and other places to ask you directly. So
yeah, they can.
Okay, quick question. I mean, Head Acoustics, we all love the Head Acoustics equipment, but few of us can afford it. But you have partners, I believe, that provide testing just like you're talking here. I mean, you put 4 heads in a car. I don't know if we could all do that, maybe one if we're lucky. But there's places that you or partners that you work with, and as well as Head Acoustics themselves, I'm sure provide the service. But there's other partnerships, I'm assuming, that you have that provide the services of using the equipment that you have so that someone
Yeah,
who's
absolutely.
just trying to begin to understand this doesn't have to invest quite yet? Is that
Absolutely. I mean, we generally, we generally communicate and work with our customers in one of two ways, and that is delivering the solutions, the hardware and software to you to do yourself, or there's sort of a consulting approach that, takes advantage of test labs and test facilities. And we have some great partners around the
okay?
world
Good.
that offer these services. Some are more geared towards automotive, some are more geared towards other, telecommunications and audio applications, but they use the head acoustics and software
Okay.
to basically perform a lot of these tests.
And you mentioned the world, so you're a global company. You have support
We are.
everywhere, I'm assuming. So, but you're also probably out at a lot of events and putting on your own. Do you have anything coming up in the near future? I am assuming the Consumer Electronics Show in Las Vegas is a place you'll be.
Head
Uh,
Acoustics will be at CES, yes.
and will you have your own place, or are you going to be at a partner's booth, or where will you be, you think?
We will be in a partner booth, but we'll have a bunch of guys walking the show, including myself. So,
Okay.
reach out and let me know if you're there, and I'll be
Yeah.
happy to meet with you.
Okay, good. Any other questions, Dave, Steve? Anything that came
No, I
up?
think that the presentation was fantastic. I mean, it leads to a lot of uh, future topics to be discussed. I
Yeah,
mean,
we'll have Jacob back. Yeah.
anything in terms
Yeah.
of the transducers or some of the mechanicals of these systems, but it's fascinating. And Jacob, you hit it right on the head. We're right at the beginning, and the applications I think are infinite. And I really applaud what the work that you guys are doing. So thank you.
Yeah,
That's
you're
good.
welcome. I would like to end on a little bit of a futuristic outlook note, because one of the things that we talked about here was privacy and zones in terms of the receive direction. And one of the things that we're actively working on, and it's unsolved as of yet, but I feel really excited about it, is a true acoustic bubble or a zone, also when it comes to what we call the sending path. So you talking inside of the car. Imagine you're on a
Oh,
phone call.
Mhm.
So yes, we can create very much of an acoustic zone in the receive path,